Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 86. It's on emission and absorption spectra. If we were to take a gas like hydrogen and put it in a discharge chamber and shoot electrons at it, it's going to give off light that looks like this. If we were to analyze that light, if we were to split it in a prism, it would look like this. So instead of being a rainbow of light, we're going to get these discrete units of light, or these discrete photons that are carrying discrete amounts of energy. And this was puzzling to scientists for a long time. We could also shine light through that discharge chamber and parts of it would be absorbed. And so this would be the absorption spectra. So most of the light would make through, but some of it isn't going to make it through. And this puzzled scientists for a long time until Niels Bohr finally figured it out. And what's happening, if we look at a hydrogen just in the first two energy levels, is that as the electron goes around the atom, as it jumps to a lower energy level, it's going to give off a photon of light. And for it to move up to that other energy or that higher energy level, it's going to have to absorb a photon. And so there are discrete colors of light that are required for it to jump up. And as it jumps down, it's going to release these discrete colors of light as well. If you hit it with other colors, it's not going to do anything. It doesn't have the right amount of energy. And so this is conservation of energy. Conservation of energy in an atom or in a nuclei when it absorbs a photon. So we call that absorption. And so what does that mean? The amount of energy in the photon and the atom or nuclei before absorption is equal to the amount of energy inside the atom or nuclei after absorption. And same thing applies with emission. And so as we give off that photon, energy is conserved. The amount of energy we had in the atom or the nuclei before is equal to both the photon and atom or nuclei after. Now this is really valuable in science because we could look at what's being given off, so we can look at the spectra of emissions from any kind of element or molecule, and it tells us what elements are going to be found inside it if we know what those energy levels are. And so if you know anything about visible light, it's all the colors of the spectrum. So as we shine it in a prism, as it moves through the glass, different wavelengths of light are going to travel at different speeds, and so it's going to split it into this spectrum. Now know this, that on the red side there's a part of the spectrum that we can't see, that's infrared light, and there's going to be UV light on the other side, and we're just seeing that visible spectrum that's going to be right in the middle. And so if we look at those energy level diagrams, for example, in a hydrogen atom, if we were to hit it with the right color of photon, so let's shine on it the right color of photon, let's say a red photon, watch what happens when it hits that electron. It jumps to a higher energy level. Now let's say it falls down to a lower energy level. What kind of color is going to be given off from that electron? It's going to be that red photon again. But what happens if we hit it with a green photon, for example, and it doesn't have the right color, doesn't have the right energy? It's never going to be able to move. Let's say we hit it with a yellow photon. What does it do? Again, nothing. And so these atoms are being bombarded by different colors of photons, but it has to be the right color. Let's say it's the right purple color. What's going to happen? It's going to jump to a higher energy level. What happens as it falls down to that ground state? It's going to give off that same exact photon. So you can model this. This is a PHET simulation. What I'm going to do is take one hydrogen atom, put it in a discharge chamber. I'm going to use a cathode ray to hit it with an electron, and watch what happens. It gets high energy, and as it falls back down, it gives off a certain color of photon. Now, if I were to hit it with not just one electron, but a continuous stream of electrons, before it's able to fall down again, it's giving off different colors of photons. So we're getting all these different colors of photons, and you can see on the spectrum on the bottom of this page, it's kind of plotting what color those photons are. So now let's do multiple atoms. Let's do a bunch of atoms. We're going to hit those with a continuous stream. And so what's happening is they're all at different energy levels, and so if we were to plot the average of all of those photons that are being given off, that's going to be that purple color we get. But if you were to do a spectrogram on it, you could see on the bottom that we're getting those bars. Now, way to the right, we've got the infrared. Way to the left is the UV. But you can see those four spectral bars that I just talked about a second ago. Now, let's say it's not hydrogen in the middle. So this is going to be a hydrogen spectrum here. I've sped up the simulation. So we're getting those bars. But let's say we change it to mercury. What are we going to get? Totally different electron, totally different energy levels, and so we're going to get different color. This is what sodium would look like. This is what neon would look like. And so when you look at a neon light and it gives that reddish color, It's the sum of all those different photons that are being given off from that neon gas. And so did you learn to describe emission, again, that's what's given off, and absorption spectra, and associate that with electron or nuclear transitions? I hope so, and I hope that was helpful.